Okay, good morning all. And so, so next week you have sessional exam, first sessional exam, and from my part, superconductivity will be included. Is it okay? So unit 3 will be included from my part for the first sessional test. Okay. So it will be just multiple choice type questions. No subjective question will be asked. So the current topic which we are learning, critical phenomena, will not be there. Only this unit 3. Okay. Okay. So we are moving to our course. Okay. I hope you can see this figure. Phase diagram of water. Okay. Phase diagram of water. So today we will learn about more about first and second order phase transitions with their thermodynamics. So this is the phase diagram of water. You see it has three portions: ice, water, and water vapor or steam. Okay. So temperature is along the x-axis and vapor is and pressure is along the y-axis. Okay. So this green dot, you see it is written to be the tipple point. Okay. Tipple point means all this vapor, ice and water, they coexist at this point. Okay. Now this blue point is normal freezing point. This blue point is normal freezing point, or it is almost 0 degrees Celsius. Okay. Here this is 0.01 degrees Celsius. That is the triple point, and the blue point is the normal freezing point. Then this yellow one is the critical point. Critical point is this one, yellow one. It is the critical point between water and steam phases. Okay, so this point separates water and steam. And what else? Normal boiling point. Yeah, so this red dot is the normal boiling point at 100 degree Celsius. Okay, so this is more or less the phase diagram of water. And in your exam, if I ask this question, so you don't have to be very specific about temperature. So you can just draw these lines, these curves. So this is one curve, this is another curve, this is another curve. Okay, these three curves you can draw, and you can point out which region is what. Suppose this is the ice portion, this is the right water portion, and below it is the vapor or steam portion. Okay. Okay, so now let us go back to the topic, which is the thermodynamics of first order phase transition, and then we will learn about second order phase transition. So let me share. Where is it? Here. Okay, so thermodynamics of first order phase transition. So this is the same figure as the one I showed you just now, but here the drawing is not very accurate, so I showed you the other figure. So there are three curves. One is the fusion curve. So fusion curve separates the solid and the liquid phase. Or in other words, what is fusion? Fusion is the conversion of, okay, let me annotate, it will be easier. So fusion is the conversion of solid to liquid. Okay. Then this is the sublimation curve. Okay. Sublimation is the conversion of solid to vapor. Okay, and the third one is the vaporization curve or vaporization line, that is the conversion of liquid to vapor. Okay, so yeah, so each curve separates distinct phases: solid to liquid, fusion, liquid to vapor, vaporization, and solid to vapor, sublimation. Okay, so these things will be required in a while. Okay, so the topic is thermodynamics of first order phase transition. So as I told you earlier that these topics are, I mean, this unit is quite dependent on thermodynamics. So you have to revise some concepts or basic concepts of thermodynamics that you learned in your BSc class. Okay. So let us assume two phases of any substance to be in equilibrium. Okay, to be in equilibrium. Dot. Then an equilibrium signifies constant temperature and pressure. What is a thermodynamic equilibrium? So that means it has to be at constant temperature and pressure. Suppose a given amount of substance is transferred from one phase to another. Okay. Or suppose transferred from a given amount of a substance is transferred from phase 1 to phase 2. Okay. At constant temperature and pressure. Okay, at some value of temperature and pressure, a substance is converted from one particular phase to another phase. Okay, let us consider pressure temperature plots for different phases of water. So just like shown here, or the first figure I showed you. Okay, since the first order phase transition involves latent heat, therefore Clausius Clapiron equation can be written as. Okay, so already I have mentioned in one of your classes earlier that first order phase transition involves latent heat L. Okay, so what is this latent heat? Latent heat is the amount of heat which is required to change the phase of a material from one to another phase at constant temperature. So when we are talking about latent heat, so it is like conversion of ice to water. Suppose conversion of ice to water at constant temperature. What is that constant temperature? That temperature is 0 degrees Celsius or 273 Kelvin. Okay, so that is the latent heat. So, and this latent heat, whenever we are talking about first order phase transition, so in that case, the latent heat is involved. So, I am writing here first order. So, whenever we are talking about first order phase transition, in that case, latent heat is involved. Okay. So, in your BSc, you might have learned about this particular equation, which is known as Clausius-Clapiron equation in thermodynamics. Okay, so Clausius-Clapiron equation, what it says? It says how much temperature change is there when you change the pressure of a thermodynamic system. Okay, so this Clausius-Clapiron equation, you have to remember this because we are, I mean, at MSc class we are not going for its derivation. So its derivation is required in BSc class in some BSc semester. So what is Clausius-Clapeyron equation? It is like the change of pressure to the change of temperature is equal to latent heat capital L divided by T temperature, and temperature has to be multiplied by the change in volume. The change in volume is Vf minus Vi. Okay, or like how much temperature is changed with a change in pressure, that you have to that is the equation for this Clausius-Clapeyron, and that particular term change of pressure with respect to temperature has this value, latent heat divided by T Vf minus Vi. Okay, So capital L is the latent heat, okay, and then dP is the change in pressure, dt is the change in temperature, Vf is the final volume, and Vi is the initial volume, okay. And T here it is written, maybe it is not so clear. So T is the temperature. So what are the various quantities in this equation A? Okay, given equation A or equation A, suppose. So equation A. Okay. So this equation you have to remember. So this equation gives the change in melting or boiling point due to change in pressure. So what this uh, Clausius Clapiron equation gives, it gives us the change in melting or boiling point due to change in pressure. Okay, so we were doing this class last year on 17th of October 2019. So this time we are delayed. It is November because your classes also started late. But I hope today is what is the date today? 7th November. Maybe by the end of this month we can finish your syllabus. By the end of this month. So I don't think we'll need more time than that. Anyhow, so let us continue. So now Clausius Clapiron equation we have understood what is this equation, and this equation involves latent heat, and first order phase transition involves latent heat. And this now we will understand each line, like this fusion line we will understand, then we will understand this sublimation line, then we will also understand the vaporization line. Okay, all these things, all these changes will be understood from the viewpoint of this Clausius Clapiron equation. So if you just do a Google search, and then you will get some more information about Clausius Clapiron equation. Okay, this is a concept from BSc level thermodynamics. Okay, so fusion. So first, let us have a look at the fusion curve or fusion plot, whatever you can call it, plot, curve, line, whatever you can call it. It's okay. So let us check the fusion plot. So now, by definition, what is fusion? Fusion means when a solid is converted to a liquid. Okay, when a solid is converted to a liquid, that is called a fusion. Okay. Suppose the volume of ice is V1 and the volume of water is V2. Then how you can write Clausius-Clapeyron equation? Okay, here it is a bit interesting because of some unusual property of water. Okay, suppose ice to water. Okay, ice to water condition. Ice has volume V1, water has volume V2. Okay. So for how can you can write Clausius-Clapeyron equation? Very simple. So dP over dt is equal to L divided by T V2 minus V1. Initially, if you remember Clausius-Clapeyron equation, it was L divided by T Vf minus Va. Okay, but now this uh, initial and final volumes are Vi and V2. Vi is the volume of ice and V2 is the volume of water. So you know that when a material in first order phase transition, especially when we are talking about first order phase transition, so there is a change in volume of the material. Okay, but it is not the case in second order phase transition. Okay, second order we'll learn later, but for first order you remember that latent heat is involved in first order phase transition, latent heat, and there is a change in volume during the phase transition. Okay. Okay, now there is a twist in this story. So what is the twist? I says greater volume since the volume of V1 of ice is greater than volume V2, ice has a greater volume than water. Ice volume V1 is greater than water volume V2. So why so? So generally we know if a solid is converted to water, if a solid is converted to a liquid, its volume increases. I mean a minute, water has lower volume than ice. Okay, let me write it down. So we have learned, so the thing is now V1 is greater than V2. In this equation for fusion means for conversion of ice to water. So this is the equation, but because of some unusual property of ice, it has a volume V1 greater than water volume V2. Okay, now you see if in equation 1, if V1 is greater than V2, then dP over dt, it will be a negative quantity. So that will be a negative quantity because this term will be negative. V1 is greater than V2, so this term will be negative, and dP over dt will be a negative quantity. So now if you read in your earlier classes about this anomalous volume of water concept, so what did you learn? We learned that water density is greater than the density of ice. Do you remember this? This is due to the like some chemical bonding, those type of things. This is due to those type of things, some chemical bonding related. So let me type here. Let me type here. Water density is greater than ice density because ice is a light material and it has many transparent or hollow structure within the ice. Ice structure is very light. Okay, because of the structure of ice, so they have lower density than water. Okay, therefore if the density of ice is lower than that of water, what will be the volume? Volume will be greater than the volume of water. So in other words, if you are converting ice into water, or if there is a phase transition from ice to water, in that case the volume is decreasing. That means ice volume is greater than water volume. Okay, so you have to remember this anomaly. Okay, you have to remember this. You have to remember this thing. Okay, water density is greater than ice density. So okay, let me write another line. So water volume is lower than ice volume. Okay, because you know volume and density are inversely related. What is what is mass? Mass equal to volume into density. Suppose V is volume, D equal to density. That means mass and volume and density are inversely related. That means if volume is high, density will be low, or in other words, if density is low, volume will be high. Okay, so that is the case. So I hope you have understood this because of some strange property of ice. Ice has greater density than water, or ice has lower volume than ice has lower density than water. Ice density is lower than that of water. Therefore, for the same mass, ice will have higher volume than water, or ice volume. Water has lower volume than ice. Okay, so I hope this is clear to you. Now you see If that is the case, if V1 is greater than V2 for ice water conversion, in that case this dP over dt is a negative quantity. Okay, if dP over dt is a negative quantity, then negative term. Okay, therefore the fusion line has a negative slope. Okay, so fusion line has a negative slope, but for other metals they can definitely. Okay, let me remove the annotation because I want to go back to the previous this plot. Okay, now let us come to this plot. Okay, so what is the so P along y-axis and water sorry, and temperature along x-axis. So what is the slope of this plot? The slope of this plot is dP over dt. Okay, dP over dt is the d capital T. So dP over dt is the slope of this pressure versus temperature. Okay. Now you see this particular plot. Okay, then let us quickly revise something. So this plot, okay, suppose x-axis and y-axis. So this plot, its slope is positive or negative? This slope is positive. Then what is a negative slope? How will a negative slope look like? Again, suppose we have x and y axis, some quantity. A negative slope will look like this. I mean, it is higher earlier, then it will decrease. And a positive slope is lower earlier, and then it will increase. Okay. So this is positive slope, and this is negative slope. Now you see the fusion line, how the fusion line looks like. The fusion line is something like this. Okay, so this is the fusion line, and the fusion line has more resemblance with this one. Therefore the fusion line has a negative slope. Okay, so have you understood this? The fusion line, which is a conversion of a solid to liquid or ice to water conversion, it has a shape like this, or the plot is like this. Therefore it has a negative slope. Okay, so why negative slope? Because we already showed that for this dP over dt, this is the slope because P is along y-axis and temperature is along x-axis. In that case, how we calculate the slope? The change in value along y-axis divided by the change in value along x-axis. So this gives us the slope. Therefore, for this plot, dP over dt will be the change in slope. Okay. Therefore, this fusion line or fusion plot is of negative slope, and therefore it looks like this. Because in that case, dP over dt will be a negative quantity. Why negative quantity? Because we have learned that the volume of ice is greater than the volume of water. That means the final volume is less than the initial volume, and therefore this dP over dt term comes out to be a negative quantity. Or in other words, the slope is a negative quantity. If the slope is a negative quantity, it will be having a like shape like this. And for any positive slope, it will be like this. So now you see the sublimation plot, it is like this. It follows the pattern of a positive slope. And a vaporization line, it has a shape like this. It also follows the pattern of this type of plot. Okay, so these two are positive slopes, vaporization and sublimation plots, whereas this is a negative slope. Okay, so I hope this concept is clear to you, and because the next two things will also be like this. Okay. Okay, so I'm removing the annotation, and I hope you have understood the fusion phenomenon. So dp over dt is a negative term. Okay, therefore the fusion line is a negative slope. Okay, so this is what we just discussed. Fusion line is a negative slope, but for other materials they contract on freezing. Therefore in such cases dp over dt is a positive term. So this is only an exception for water. Okay, but if you consider any other material except water, so their volume will increase. Okay, okay, let me type here. Let me annotate it. For materials other than water, liquid has greater volume than solid. So fusion line will have a fusion line will have a positive value. Okay? Water is only exception. So in water, fusion line has negative value. Okay, fusion line has negative slope. Okay. Okay. So now let's move to vaporization. So what is vaporization? So vaporization is this line. So that is the conversion of a liquid into vapor. Okay, liquid into vapor transition is known as vaporization. So you know the definition already, because you have also learned these definitions in earlier classes. So when a liquid is converted to vapor, the process is called vaporization. Okay? Suppose the vapor has volume V3 now. Okay, vapor has volume V3 and liquid had volume V2, because it is also considered earlier here. Water has volume V2, and now this water is converted to vapor, and which is having a volume V3. Therefore, how you will write the Clausius-Clapiron equation? The Clausius-Clapiron equation, I hope you can understand this. dp over dt is equal to LVAP. Okay, let me just write it. So dp over dt equal to L VAP. I am writing here VAP. VAP stands for latent heat of vaporization. That is LVAP. Okay, latent heat of vaporization divided by T V3. Okay, this is 3. Not written very well. 3. This is okay. V3 minus V2. Okay. So dp over dt is equal to LVAP divided by T V3 minus V2. Okay. So this is the Clausius-Clapeyron equation for the vaporization process. So just you have to change the volume values, and in place of latent heat you can write LVAP, or latent heat of vaporization. Here V3 is greater than V2 because the vapor has now a larger volume than the liquid or the water. Now if you see this equation 2, if V3 is greater than V2, then dp over dt will be a positive quantity. Therefore this dp over dt is a positive quantity. Okay, and now if dp over dt is a positive quantity, it is nothing but the slope of this plot. It is nothing but the slope of this plot. So as already I mentioned, this is a positive, this plot is having a positive slope. Okay, why? Because it is having it is increasing like this. Okay, it is not a very straight line, but still it is increasing. So dp, p along y-axis, temperature along x-axis. So dp over dt is having a positive slope. Okay. Therefore, dp over dt is a positive quantity. Okay, and therefore this sublimation plot or sublimation line is sublimation. I mean, dp over dt is a positive quantity. Therefore, the sublimation line it follows this pattern. Okay, this pattern means from left to right. Now, if the vapor is considered to be an ideal gas, okay, if the vapor is an ideal gas, in that case, what will happen? So you already know what is ideal gas equation from thermodynamics. You already learned. So PV3 equal to RT. So this is the ideal gas equation. Okay, if the vapor is that to be okay. So what is an ideal gas? So this definition of an ideal gas is if the equation of state is like this, PV equal to RT, then the gas is an ideal gas. In that case, and vapor is okay, is an ideal gas, and another thing, this V3 or the volume of the vapor is much larger or very greater than the volume V2. In that case, what we can write? In that case, we will write this dp over dt from equation 2. So dp over dt will be equal to LVAP divided by temperature multiplied by V3 minus V2 we have. Okay. But now we are also considering that V3 is much greater than V2. So if V3 is much greater than V2, therefore we can simply omit the V2 term and we can write it as TV3. So dp over dt is equal to LVAP divided by TV3 because V3 is much greater than V2, LTV3. So now dp over dt is equal to LVAP divided by TV3. So V3, what is V3 from here? From this equation, V3 is, okay, let me just annotate here. Sorry, this is nothing. V3 is equal to RT over P. Therefore, T multiplied by V3, V3 is RT over P, RT over P. Therefore, it will be PLVAP divided by RT square. Okay, therefore, dP over dt is equal to PLVAP divided by RT square. So, this is a simplified form or a special case, rather you can say, in the process of vaporization. Okay, so first you find the general equation of Clausius Clapiron equations general form, and from there you consider the vapor to be an ideal gas and also consider that the vapor is having a volume much larger than the volume of water. Okay, so after that V3, you substitute the value of V3 and then you can calculate the dp over dt. You can calculate. Okay, so it is a simplified case. Okay, so not that difficult, again, very easy. So again, the last process is sublimation. Okay, so sublimation is the conversion of solid into vapor form. Okay, so again, if we come back to this plot, so you see this is the sublimation line or sublimation plot. So and it is the conversion of solid into vapor. Okay, the sublimation plot separates the solid phase from the vapor phase, or in other words, if a solid is converted to vapor, that is known as sublimation. So let us check what happens to this Clausius-Clapeyron equation in the sublimation process. So when a solid is converted to a vapor, it is called sublimation. Okay. So now what we consider the volume of the solid phase to be, it was V1, or the ice phase, it was V1, and the volume of vapor, it is V3. Okay, because the liquid volume was V2, so V1, V2, V3. So then what is the uh, then what is the dp of, how we can write Clausius-Clapeyron equation? So dp over dt is equal to L divided by T, V3 minus V1. Okay. Uh, the volume of vapor V3 is greater than the volume of solid V1. Okay. Of course, we all know solid, vapor has greater volume because gases or vapor can extend to a much larger volume than that of a solid. Therefore, V3 is greater than V1. So we refer to equation 3. In this equation 3, V3 is greater than V1. Okay. And how you can write equation 3? Okay, therefore from equation 3, V3 is greater than V1. Then dp over dt is a positive quantity. Okay, then dp over dt is a positive quantity. Okay, and if dp over dt is a positive quantity, and I am again going back to this plot. See the sublimation. You see the sublimation plot. It is also having a positive slope, unlike the fusion plot. In the fusion plot, it is like this. It is having a negative plot. But sublimation is having a positive slope, and vaporization is also having a positive slope. Okay, only fusion line is having a negative slope. Okay, so this time sublimation slope is also positive. Why? Because for sublimation, dp over dt is also a positive quantity. Again, we may take a special case into consideration. If the vapor is considered to be an ideal gas, in that case, PV equal to RT. Okay, PV3, sorry, PV3 equal to RT, just like the previous case of vaporization. So V3 is equal to RT over P. Okay, and now if V3 or the volume of the vapor is considered to be much larger or much greater than the volume of the solid, that means V3 is much greater than V1. In that case, how you can write this equation 3? Equation 3 you can write as dp over dt. Equation 3, dp over dt, L divided by TV3. Okay, because V1 is a much smaller quantity as compared to V3, so L divided by TV3. But now this L or the latent heat, it will be written as LSUB. LSUB means short for sublimation. Okay. So V3 is equal to RT over P. Okay. Therefore, T multi T V3. So VT is RT over P. So LSUB by RT, TRT over P. Therefore, P LSUB divided by RT square. Okay. So this is the simplified form of this Clausius-Clapeyron equation, considering the process of sublimation, and the considering again the vapor is an ideal gas and the vapor's volume is much greater than the volume of the solid. Okay. Okay, so that is more or less about the, not more or less, I mean, we are almost done with the topic of thermodynamics of first order phase transition. Okay. So what we have to consider, we have to consider that we have to consider the Clausius-Clapeyron equation. First, remember Clausius-Clapeyron equation, and which is having this form. So you have to remember this form. Okay. So dp over dt is equal to L divided by T, Vf minus Vi. L is the latent heat. Okay, because you also have to recall that in first order phase transition, latent heat is involved, and also there is change in volume. Okay, so Yesterday also we discussed about this when we were, maybe I can show you. Let me just, where did we show? So this note I will share with you, but not now, maybe after a few days, after, because when we'll have done most of the topics. Where is it? So, where is it? Okay, so we discussed anyway. So first order phase transition involves latent heat and change in volume. Where is it? Yeah, here maybe first order discontinuous phase transition characterized by discontinuous change in entropy at a fixed temperature. The change in entropy corresponds to latent heat. Okay, therefore this first order phase transition involves latent heat, and also there is volume change. Okay, although we have not mentioned the volume change. And second order phase transition is another thing. We will also learn about it. And therefore, when we are learning about the thermodynamics, we have the latent heat, capital L, and the volume change. Okay, so this is the expression for first order phase transition, which is understood by this Clausius Clapiron equation. Okay, so once you recall this equation, Clausius Clapiron equation, then the things become easy. You just refer to this water's phase transition diagram, where you plot pressure against temperature, and you have three plots: sublimation, fusion, vaporization. Okay, and don't forget, okay, because I have seen while checking exam copies of some students, they mess in this figure. Somebody writes solid to be here, somebody writes solid here, liquid here. So that is a like wrong thing. Okay, then the whole meaning gets changed of this. I mean, this figure becomes meaningless. So you have to be careful while writing these names: solid, liquid, and vapor. Okay. So the change in solid liquid, these lines you also have to remember. And once you know this figure correctly, and once you know this Clausius Clapeyron equation correctly, then the rest of the things are easy. So what is fusion, what is sublimation, what is vaporization, those things become easy. Okay. So the figure, I will share this note because some things maybe you will not be able to understand because of handwriting, but otherwise this note is quite comprehensive. So almost all phase transition notes are here. From this is from last year's notes. Okay. Okay, so second order phase transition is a bit mathematical. I mean, the thermodynamics of second order phase transition is a bit mathematical. So that we can do from beginning in the next class. Okay, so I'm not going to start it today because uh, for today only first order is fine. So second order we can do in the next class. Okay, so okay, in 5 minutes. So I hope you all know. So your sessional unit 3 is included in your first sessional, and you study everything. Okay, the superconductivity. Of course, there will be only multiple choice questions. There will not be any subjective type questions. Okay. So, and any news on your like when you want to come for practicals? So, have you decided anything yet? Or is there any notice from the USTM like when you want to go for practical in the campus? So you have not decided yet about practicals? Anyway, no problem. So that's your decision. Okay, I think so. We are done for today's class, and